Assalamualaikum warahmatullahi wabarakatuh. Hmm, uh, my name is Muhammad Afiq Hafizuddin bin Azman, uh, and I am a PhD candidate from the Faculty of Industrial and Manufacturing Engineering Technology. So today I'm gonna present on my research proposal. Uh, the title of my research proposal is Investigation of Ultrasonic Vibration Effect on Shape Recovery and Microstructure of 4D Printed Shape Memory Polymers. So today I'm gonna go through this research proposal. Behind this is just the gap it addressed, the methodology that I plan to employ toward the research, and the outcome that I expected to deliver over the course of the program. Okay, let me the next slide. So let me begin with the big picture. So the field of 4D printing has emerged as a natural evolution of conventional 3D printing, where 3D printing creates static objects with fixed geometries. For 4D printings, introduce the dimension of times, which producing structures that can change their shape, properties, or functionality in response of external stimulus. So the material that makes this possible are called shape memory polymers, or SMPS. They are programmable material that you can deform them into a temporary shape, and when we triggered with a stimuli, they can snap back to the original shape or pre-programmed configuration. Now we look on the executive summary and the research background. So the current frontier, or what I am calling the evolution of actuation, has largely relied on broad stimuli, which such as heat applied from an oven, moisture from the environment, or exposed to light. These methods work, but they are lack of precision. They apply stimulation uniformly across the structure, making selective localized actuation nearly impossible. So the proposed frontier of this research is to use ultrasonic vibration as the stimuli, as a precise, localized and non-contact stimulus for actuate the 4D printed SMPs. The core focus is on PLA and TPU-based polymers tested in between 20 to 40 kHz frequency range. The overarching aim is to establish the fundamental mechanism, optimize parameters, and correlation model for UV-induced shape transformation. So next is the problem statement and the literature context. So what is exactly wrong with the current state of field in 3D printing? Allow me to be specific. There are three fundamentals bottlenecks that prevent SMPs from reaching their potential in real-world application. First is the conventional stimuli, such as heat, moisture, or lack of precise spatial localization. So when you hit an entire structure, every part of it wants to recover simultaneously. So you cannot tell one section to move while another stays still. Second is the response of the SMPs under cyclic high stress condition is poorly predictable. This limits their deployment in any application, such as aerospace or medical device, where you need a reliable, repeatable performance over thousands of actuation cycle. Third is the repeated thermal cycling degrades the microstructure of these polymers. The very mechanism used to trigger them over time can destroy the functionality of the SMPs. So, in terms of the literature context, literature corroborates this that from Panoma et al. In 2002 and Pokras et al. In 2004, both observed that current research is bottlenecked by the reliance on broad application thermal stimuli. This leads us to the missing linking, where there is a critical absence of understanding regarding ultrasonic vibration as an actuation mechanism. The imperative is clear. We need a mechanistic understanding of how frequency mechanical energy translates it into localized thermal and structural actuation within these polymers. So next we move to the research gap, metric and novelty. So to make the research gap absolutely explicit, I have mapped the existing literature against 4 critical dimensions: 4D printing, SMP integration, ultrasonic manufacturing, and the last one is the ultrasonic actuation of FDM printed SMPs. Looking at these metrics, we can see that Alam et al. And Pokras et al. Have worked on 4D printing with SMP integration, but neither investigated ultrasonic simulation. Wang et al. And Peng et al. Also explored ultrasonic interaction with polymers and manufacturing process, but not in the context of 4D printing or shared memory actuation. The last column, which ultrasonic actuation of FDM SMPs, is entirely empty in the existing literature at this time. This proposal fills out that column. This is not a marginal improvement on existing work. This is the first systematic study to treat ultrasonic vibration as a primary control stimulus for FDM printed shared memory polymers. So that is the key of the novelty of this research. So next we move to the research question and objective. From the gap that have been listed from previous literature, I have derived 3 tightly aligned research questions and their corresponding objective. Research question 1 asks, how does ultrasonic vibration actuate and influence the shape transformation and recovery of SMP printed samples, which is answered by the objective 1 by analyze the effect of the ultrasonic vibration and its influence on the actuation of SMP printed sample using high-speed and thermal cameras to observe. Second research question is, how can we formulate the relationship between ultrasound parameters and printing parameters to obtain optimal mechanical properties, microstructure, and the shape recovery? So it is answered by the objective 2 to address through a rigorous statistical analysis known as ANOVA based evaluation of the interaction between these variables. The third one is, why is ultrasound vibration a viable alternative to the traditional external stimuli, which is answered by the objective 3 is by establishing statistical correlation between UV parameters and material performance, building the scientific justification for the entire approach. So I want to highlight the logical chain here, which we first observe, then we optimize, and finally we explain by justification and discussion. This sequence ensures that by the end of the program, we do not merely know what happens, we know why it happens. Next one is the research scope and boundaries. It is actually important to be precise about what this research does and does not cover. The scope is defined clearly across 4 dimensions. In terms of material, this study is confined to thermoplastic SMP filaments compatible with FDM processing, specifically PLA-based SMPs, TPU, PTFE, and PCOE. These were chosen because they represent a broad spectrum of mechanical and thermal responses. and are commercially available in a filament form. In terms of equipment, all fabrication will be conducted on a desktop FDM system, fused deposition model. This is a deliberate choice. It ensures reproducible, control manufacturing condition, and keep the study accessible for future application. The stimulus is restricted to piezoelectric arsenic vibration in the range of 20 to 40 kHz, and the analysis framework is statistical DOE, ANOVA, and correlation modeling. What is explicitly out of scope includes large-scale industrial manufacturing, long-term cyclic fatigue testing, real-time closed-loop control system, and in vivo biomedical testing. I want to be transparent about these boundaries. They are not the weakness of this proposal. They represent a focused, achievable scope for a PhD program, and they leave clear pathway for future work. One important note at the bottom of this slide is conventional thermal stimulation will be included in the study, but strictly as a comparative baseline, not as a primary stimulus. Next, we go to the conceptual framework. Now, let me explain the intellectual architecture of this research, what I call the chain of effect. This framework describes the causal pathway from input to outcome. It begins with the ultrasonic parameters, consists of frequency, intensity, and the exposure time. They are the independent variable that we control. When applied to an SMP sample, they drive SMP actuation, the conversion of high-frequency mechanical energy into localized thermal and vibrational energy within the polymer matrix. This localized energy input triggers microstructural changes, specifically shift in porosity, molecular alignment, phase transition, and the degree of crystallinity. These microstructural changes in turn determine the mechanical properties of the printed sample, its tensile, flexural, compressive, and impact performance. And all of this fit into the final micro behavior, the shape recovery ratio, transformation response, and recovery time. This is what we ultimately measure and optimize. The reason this change is important is that it prevents us from treating this as a black box. Every panel in this diagram corresponds to set of measurement and characterization technique and methodology. We are not measuring outputs, we are tracing the mechanism from the cause to effect. Next is the methodology flowchart. This is structured into 6 sequential phases spanning approximately 3 years of active work. First one is conceptual and planning, which is completing the literature review, procuring material, and bounding these experimental parameters. This phase is substantially complete. I have reviewed over 27 key references, and the material selection and parameter changes have been identified. Phase 2 is the test rig fabrication. So, at the time being, the machine of FDM does not arrive yet. So, by next week, it should arrive at the Phase 3 is the actuation study, addressing objective 1. Here, FDM printed SMP samples are subjected to UV frequency from 20 to 40 kHz with shape transformation recorded by thermal and high-speed camera. Notice the feedback loop in the flowchart. If modifications are needed to the test rig or protocol, we look back to the Phase 2 before proceeding. Phase 4 is optimization and characterization, addressing the objective 2. Using the optimized UV parameters from Phase 3, we now vary printing parameters, layer thickness, which consists of layer thickness and build orientation, and conduct the full DOE matrix with complete mechanical and microstructural characterization. Phase 5 is the correlation analysis, addressing objective 3, which consists of statistical relationship between UV parameters, microstructure, mechanical properties are established. Phase 6 is the dissemination, which is thesis writing and journal publication. So as you can see, this is the infographic of the experimental setup and the system integration. Let me now describe the physical experimental setup in detail. The system consists of 4 core components working in content. At the center is the desktop open source FDM 3D printer. Attached to it build platform is a piezoelectric transducer configured in horizontal vibration mode. This transducer is driven by a function generator, capable of converting a standard of 60 Hz electrical input to high frequency signal in the 20 to 40 kHz range. An oscilloscope monitors the signal in real time to ensure the frequency and amplitude stability throughout each experiment. Critically, we have 3 measurement instruments observing the sample during actuation: a thermal camera to map the localized temperature distribution on the SMP surface, a pyrometer for point temperature measurement, and a high-speed camera to capture the kinematic dynamics of shape transformation. The combination of thermal and high-speed camera imaging is particularly powerful. The thermal camera tells us where and how much heat is being generated by the viscoelastic dissipation, while the high-speed camera tells us how the mechanical shape response unfolds over time. Together, they allow us to correlate thermal input with mechanical output at the same level. So next, the DOE of the framework. The experimental design follows a full factorial design of experiment approach, which allows us to systematically evaluate not just the individual effect of each parameter, but the interaction effect between them. On the inside put, we have 2 categories of variables. The ultrasonic parameters are frequency at 20, 40, and 60 kHz, intensity at 1 to 3 watts per square centimeter, and exposure time at 5, 10, and 15 minutes. The printing parameters are layer thickness and build orientation. This gives us a 3-cube metric, 27 experimental treatment combination, each compared against a strict non-ultrasound control baseline. The DOE engine systematically evaluates every combination, generating a rich dataset of outputs across these 3 categories. The first output category is mechanical, which consists of tensile strength, yield strength, elastical modulus, and flexural properties. The second one is the microstructural, consists of grain size, molecular alignment, phase transition, and the third is the behavioral of the shape recovery percentage and recovery time. We can also see a preliminary data table embedded in the DOE engine. This illustrates the kind of output we expect. So next is the statistical analysis plan. The statistical analysis plan flows in 3 stages, each building on the previous one. The first stage is the analysis of variance, or ANOVA. This will assess the statistical significance of each ultrasound parameter and printing variable, as well as their interaction. The significant threshold is set at P less than 0.05. So ANOVA will tell us which parameter matter and by how much. The second stage is principal component analysis, or PCA, which potentially hundreds of data points across 27 treatment groups and multiple dependent variables. The dimensionality of dataset can become unwieldy. PCA reduces this complexity by identifying the principal components, the combination of input parameters that explain the most variance in the outputs. This allows us to visualize the multidimensional response landscape in a lower dimensional space. The third stage is multivariate regression modeling. Using the findings from ANOVA and PCA, we construct a predictive mathematical model that quantifies how the combined factors, frequency, intensity, and exposure time, together determine shape recovery and structural integrity. This model is the intellectual output of phase 5, and it is what will form the basis of the design, the guideline, and the journal publication. The final output of this pipeline is a Pearson correlation coefficient and optimized predictive models, tools that any engineer could use to design a UV actuated 4D printing process without needing to repeat this full experimental program. So next we go to the characterization and measurement technique. The characterization program is organized into 3 parallel tracks, each corresponding to one output category in the DOE framework. For microstructural analysis, we will use SEM to image surface morphology and assess polymer chain alignment at the interface between deposited areas. XRD will quantify the crystalline structure and the degree of crystallinity, which is particularly important for PCOE and PLA-based sample. The DSC will measure the thermal properties, including the glass temperature, in glass transition temperature, which is critical threshold that UV must exceed to trigger the shape recovery. For mechanical testing, all specimens will be prepared and tested according to the relevant ASTM standard. For tensile properties, for Young modulus, for compressive strength, for flexural strength and impact resistance. For shape memory behavior assessment, sample will first be pre-deformed, either bent or twisted, to establish a temporary shape. UV will then be applied and will quantify three metrics: the pre-deformation shape retention limit, the shape recovery percentage, and the transformation recovery time under UV excitation. These three metrics collectively define the shape memory performance envelope of each material under each UV emission. So the expected outcome from this research, I would now like to be explicit about what this research is expected to contribute to the field and how those contributions translate into the real world impact. At the scientific knowledge level, this study will deliver the first fundamental understanding of UV-induced actuation mechanism. At the microstructural level, this is a knowledge that does not currently exist anywhere in the open literature. It expands smart material science beyond the thermal dependency, opening entirely new design possibilities. At the methodological optimization level, we will establish structural properties, stimulus relationship, and validate predictive mathematical models. These models are not merely academic. They provide engineers with actionable design guidelines for any future UV-actuated 4D printing process. At the industrial application level, the outcome directly enable fast, localized, and non-invasive shape shifting capabilities. The future impact pathways are threefold: expanding smart material science beyond thermal dependency, providing design guidelines for scalable and reliable FDM printing of SMPs, and opening pathway for real application in aerospace morphing structures and smart healthcare implants. This research is directly aligned with the nation vision for Industry 4.0 readiness and material innovation, contributing to the nation's ambition to move up the value chain in advanced manufacturing. So, as you can see, this is the timeline and a milestone for my research. And this last one is the publication and the conclusion. So, in conclusion, let me talk with this proposal. Ultrasonic vibration is not merely an alternative stimulus. It is a transformative mechanism capable of providing the localized, rapid, and controllable actuation required to push 4D printed shape memory polymers into scalable real-world industry application. I am confident this research will make a meaningful and lasting contribution to both the scientific community and the advanced manufacturing industry. Thank you very much.